Something really loud noise.
There you go. Let's see, warm up. Let's see, x to the fourth when x is 3. That's saying figure out what 3 to the fourth is. And hopefully basic exponent rules. An exponent represents how many times you're multiplying this base by itself. So this is saying take 3 and multiply it by itself 4 times. 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, plus 3 is exactly 81. Okay. A squared, when a is negative 6. How many people got negative 36?
Wait, what?
How many people got negative 36?
I did not.
Well, if you didn't get negative 36, what did you get?
Positive.
So which is it? Is it negative or positive?
Positive.
Why is it positive and not negative?
I'm sorry.
I didn't realize we were doing the whole
Because 2 negatives is a positive. Well, if you got a negative 36, how'd you get negative 36? How'd that come up? Did you try this on your calculator? Negative 6 squared?
In fact, I did.
And what did your calculator tell you?
36.
I can guarantee if you type that into your calculator, you got negative 36. Guaranteed. You got negative 36, not positive 36. The correct answer is, as we know, should be negative 6 times negative 6. Negative times a negative is a positive. This is the correct answer. But I guarantee your calculator thinks that this is negative 36. So, why is that? Well, your calculator sees negative 6. It doesn't really do negatives well. What it thinks of as a negative, it thinks that this is negative 1 times 6 squared. That's how your calculator handles this. That's how the programming is set up. Well, your calculator also is very, very good at following orders of operations. PEMDAS. What is, if I want to simplify this using my order of operations, negative 1 times 6 squared, what should you do?
Exponent.
Exponents come first. So your calculator is doing 6 squared is 36. And multiplying that by negative 1 and getting negative 36. Well, we know that's wrong. This is not what we want it to do. So does anyone have a suggestion for how we can convince the calculator to actually do it correctly? Courtney?
Instead of typing the exponent, you do you type in the base.
Okay, you could do negative 6 times negative 6. Sure, that's one way to get around it. But what if this exponent is really big, and that's going to be a lot of like that same thing multiplied out? Does anyone have an idea of what else we could do to convince the calculator to actually multiply the right stuff? Anyone?
Make the exponent negative.
What could we do to convince the calculator? It's an easy thing to do. To make this original thing, to make the calculator actually do what we want it to. What could we add in? Okay, don't type the negative. Well, that's not really good because I want it to be negative. Like I want to multiply negative 6 by itself twice. But clearly if I type it just like this, the calculator won't do it right. Like, so how can we convince the calculator to actually do it correctly? Jack?
Doing negative exponent?
Negative exponent? No, we're going to see actually negative exponents mean something very distinct, and that's not what we want. Negative exponents actually tells us to do reciprocals, which we'll see in a couple days. That's not what we want. Joe? What if we convince it to use PEMDAS correctly and throw parentheses around this? Now what's the calculator think to do? Something squared. Whatever is being squared, now the negative 6, now the negative and the 6. Now the calculator thinks, okay, take whatever is inside these parentheses and multiply it by itself. So now the calculator thinks, oh, maybe I should do this. Or maybe I should have instead, negative 6 times negative 6. By throwing these parentheses in around your negative sign, you'll convince the calculator to actually multiply the right things together. Which is negative 6, it now correctly knows is positive 36, which is correct. The moral of this story here is that as we see negatives and we work through, seeing negative signs, and especially when it comes to exponents, is that that parentheses are your friend. And that the more we can use, the better off the more likely your calculator is to give you the right answer, and to more likely you'll organize yourself correctly. Okay, so when we see negatives and we want to raise a negative to the exponent, the moral of the story is let's make sure that we have parentheses in there, and then we'll make sure we get to the problem. Okay. M to the third, when m is negative 5, most of you, if you did it by hand, correctly said it's negative 5 times negative 5 times negative 5. Negative times negative is a positive 25. Positive 25 times negative 5 is negative 125. Okay. Last but not least, we have this little mini storage box and a food storage container. It's the shape of a cube. What's the volume of this container if one side is 4 inches long? And also note that the volume of a cube is equal to the side to the third power. Well, if this is saying the volume is equal to 4 to the third power, 4 times 4 is 16, times 4 is 64. This has got a unit attached to it. If each side is 1 inch long, what's the volume? What should we call the unit for the volume? Well, we're cubing it, so we'll do inches cubed. It's the same story as if you want to find the area of a square. The area of a square is side squared. So then the unit that goes along with an area is like inches squared. You have a volume, you multiply something by itself 3 times, we'll take that unit and multiply by itself 3 times. So you have inches cubed for a volume. Quick review of old exponent ideas. Okay. The goal for today is to take these old properties and now we're going to apply them more generally. Or what happens if we want to write our expressions in what's called exponential form. How do we take things that are numbers that are big groups of the same things multiplied together? How can we write them in an easy to read, more compact way? And that's kind of what the whole purpose of these exponents are. It's take really large numbers and be able to write them so that we can actually deal with them instead of having just these ginormous things that go on forever or seemingly forever. We're going to have 3 properties today. We're going to start by looking at exponents in terms of multiplication. Anyways, we're going to end up having 3 properties today of exponents. We're going to focus on properties that deal with multiplying up. So the first one is the products of powers. Or if I have products being multiplied, if I multiply a bunch of things raised to a power, how do I deal with that? We're going to start with a concrete example, and then I'll have a kind of a more symbolic formula for you. So my first example is, what if I have, say, what if I want to know what this thing is? How about 3 to the 4th times 3 to the 3rd? How can I simplify this more? I have a product, a multiplying of 2 things raised to a power. Okay? Well, one way to handle it is using the definition of an exponent, which is 3 to the 4th. What's another way to write 3 to the 4th power?
3 times 3.
3 times 3 times 3 times 3. What's 3? So it's this stuff multiplied by what's 3 to the 3rd power?
3.
Right, well, how can I write this thing? Now, this is just a bunch of 3's all multiplied together. How can I write this using just one exponent? What's this? What power of 3 is this all to?
3 is 7.
1, 2, 3, 4, 5, 6, 7 power.
I am so good.
Does anyone see maybe a quicker way to arrive at 3 to the 7th power? Rope? You could have just taken 4 plus 3,
I'll write it.
and that's the same as 7.
I'm not. That's the part.
Power of product property says the following. It says that for like bases, base being, if I have something of this general form, base being the bottom, And what's called the superscript, what's above, is called an exponent. If you have like bases, then the following is true. I multiply those same bases together. Multiplying the exact same base is the same as just combining it with one base and adding whatever those exponents were. So you can remind yourself, if multiply in words, multiplying in like bases, add the exponents. In symbols, in words. If multiplying like bases, then add the exponents. If these things aren't the same, can't we go combine the exponents? If you had like 3 squared and 6 squared, that's not, you can't combine those things because the bases aren't the same. It wouldn't be like 9 to the 4th or something. It's not the same. The bases have to be the same. So using this property, this idea, if I find like bases, I can combine the exponents with addition. So I'll do the first, say, a couple with you here. 4 to the 7th times 4 to the 6th. You could write out all those 4s and count how many there are. Or maybe a better way might be use this property. The bases are the same. You can just add the exponents. So what should this simplify to me? 4 to the 13th. I didn't mention, but recall, what is it if I give you a number and I don't have an exponent appearing? What's the exponent that goes along with it?
1.
So if you don't see an exponent, it can help to plop that 1 in if you don't see it, to use this property. So what should this simplify? What should B simplify to? 8 to the what power? 8th power. 5 plus 1 plus 2 is 8. Okay. Negative 3 to the 3rd times negative 3. Well, this is like, say, to the 1st power. So it's negative 3 to which power? Add them together. Note that I left the negative 3 in parentheses. It's for that same reason that we had in the warm-up. If I have a negative sign, make sure we don't want to just get rid of it. We're going to keep that along for the ride and make sure we put it inside parentheses. Also notice that since these exponents talk about multiplying, they're like hidden multiplication, behind the scenes multiplying. We want to keep that negative in there, even if we're just combining these two things together. Because this isn't just negative 3 times negative 3. It's actually like 3 of these and 1 of those. We're going to combine those together. We can simplify this negative sign in the end. E, this was supposed to be a parenthesis. This was supposed to be like a part D, not like D times all that stuff, if you were wondering. What's our answer here? B to what power? 11, I believe. 1 plus 3 plus 5 plus 2. 11 power? Okay. So if we're combining with multiplication, same base with multiplying, we'll add the exponents. Well, but that's not the only thing we can do. We could also, well, as you see on the backside, maybe we have powers of other powers. Oh boy. How would you do, like, say, actually, how would I handle this? 6 to the 4th squared. Well, 6 to the 4th is a pretty big number. It's not a small number. I probably don't. It's too big in effect for me to want to spend my time multiplying what 6 is to itself 4 times, getting a big number, and then squaring that thing. I'm going to leave this in exponential form, in exponent form. Well, following my rules, my definition of what an exponent is, this is exponents say take whatever is right underneath it and multiply that thing by itself the exponent number of times. So working our order of operations rules, parentheses, I'm going to work outside in. So by definition, this is saying take whatever's inside these parentheses and multiply it by itself this many times. So this is saying take 6 to the 4th and multiply it by itself twice. 6 to the 4th times 6 to the 4th. What should this be in exponent form? 6 to the 8th. Using our previous rule, you could break this down farther and say this is 6 times itself 4 times. And this is 6 times itself 4 times and count all the 6s. You could just use that previous rule from the front side and say, well, 2 bases that are the same, or multiplying, we just add the exponents. This is 6 to the 4 plus 4, which is just 6 to the 8th power. Kind of like before, does anyone see maybe a shortcut? Yeah. Another way to get 6 to the 8th by taking this setup. What's 4 times 2? 8. Power of a power. If we have exponent of more exponents, we can multiply the exponents. In symbols, so in symbolically it would be for, let's see, if you had a to the x all to the y, that's the same as a to the x times y. Or in words we could say for powers of powers, multiply the exponents. It may be that property in words. So rather than counting out these, rather than going by the definition, we can use this shortcut method to come up with what the correct exponent form would be. So like 7 to the 4th, all to the 5th, that should be what? Same as 7 to the 4 times 5, which is the same as 7 to the 20th power. Negative 3 to the 4th, all to the 2nd power. That looks a lot like that example I just did. What should this one be? Negative 3 to which power? 8th power. Let's see. Y to the 3rd power, that's what, y to the 6th.
Wouldn't it be 9?
Oh, I shouldn't have added them together, right? I should have multiplied them. Yeah. Nice catch. Actually, the 9th power, don't add them. Power of power says multiply them. 3 times 3 is 9. And our last one. That's my favorite one. Okay. Okay, let's break this thing down. So I have, not only do I have parentheses, but I have brackets. Brackets are just fancy parentheses. Anyone, off the top of their head, can anyone think of a reason why I'd want to use 2 symbols that mean the same thing but look different? Why would I want to do that? Brooke? Yeah. What if I already use parentheses once? Do you think it's going to be easier or harder to tell what all these things mean if I use different symbols, or if I use just the same thing, just blend it all together? Yeah, if I just kept using parentheses, the parentheses, to me at least, they might just blend all together. I don't really know what's what. So I'm going to use like brackets and parentheses so that I can tell the difference between the two. And you could use maybe parentheses for the 3rd one, just so you can tell where all the layers are going to be. You can use fancier brackets if you wanted. All it is just how to group and how to tell the difference between the groups. Anyways, we're going to work outside in. So let's see. Since I have 9, I have whatever's inside of these brackets raised to the 9th power. And what's inside of them? N plus 8 squared. So I have n plus 8 squared times itself 9 times. So how many n plus 8s do I end up having multiplied all together? 2 times 9, which is 2 times 9, which is 18 of them. Okay? This is the final answer. There is nothing else you can do to this. Well, as far as exponent form is concerned. What I guarantee that after we go through this next property, I guarantee that about half of you are going to try to do this. And I'm going to do it in blue here because it's to highlight how it's different. About half of you are going to think, oh, well, I have this exponent here, and this has got to be the same as this. Hopefully you don't do this. This is not something that you want to do. Okay? The reason is this. The reason is that exponents are all multiplying things. Things are multiplying all together the same. That is not multiplying. This is adding. Different operations. Exponents go together with multiply. If you have anything other than multiply, well, tomorrow we'll see divide and multiply basically the same. But if you have adding or subtracting, that's not a multiply rule. Adding does not really go well with exponents. So if I see adding, that's like a big stop sign. Stop. Don't go there. Maybe you can go old school and like cross your finger. No, don't go there. Exponents and adding don't get along. So we're not going to go ahead and try to distribute that little exponent if there's adding inside. However, if there's multiplying inside, we actually can. So I think this is some of the reason why people will get that and what's coming up next confused. Is that if there's only multiply, multiply and exponents go along really well. We can actually handle that. Okay. Power of a product. Or if I want to take something that's multiplied together, how about we do, let's see, last time I did what, 2x squared. The third power, I think I did. Power of a product, or of two things, or of a group that's all multiplied together. Note the difference between this example and this example. Add in here, bad. Multiply here, good. Kind of the same game. Exponents, they take whatever's inside and multiply it by itself the exponent number of times. This should be the same as what? 2x squared times 2x squared times 2x squared. Whatever's inside, multiply it by itself this many times. What's 2 times 2 times 2 as an exponent, with an exponent form? What's 2 times 2 times 2 written as an exponent, with an exponent? Okay, 2 times 2 times 2 is 8. However, that doesn't have an exponent. That's not an exponent of 2. What power of 2 is 2 times 2 times 2? We multiply it by itself 3 times. What's the exponent? What's x squared times x squared times x squared? What exponent goes along with that? 2 times 2 times 2. Well, 2x squared times x squared times x squared. If I multiply bases, what do I do to the exponents? Go back to the front side. If I multiply the same base, what do I do to the exponents? Add them. 2 plus 2 plus 2 is 6. I'm going to ask you exactly the same question. Can you think of a quicker way to have gone from here to there? What would be a quicker way to have gone from here to here? What's power of power say we should do? What do you do to the exponents? Power of power. Multiply. What exponent goes with this 2? This one doesn't have 1, so we'll put a 1 in. What's 1 times 3? What's 2 times 3? 6. If there's only multiply, exponents and multiplying get along. If there's only multiplying, you can think of it as distributing this exponent. If there's adding or subtracting on the inside, stop sign. Not allowed to do it. This property only works if there's only multiplying, and tomorrow we'll see it also works with division. It does not work with adding. It does not work with subtracting. So you could have done, we could have thought of this as 2 to the 1 times 3 times x to the 2 times 3. We could have thought of it like this. It works because there's only multiplying. And I can't stress that enough. The difference between only multiplying and there's some adding inside. Adding, no good. Can't do exponents with addition. Can't just start distributing. In general terms, it says that how about a times b to the x is the same as a to the x times b to the x. It says that for, or in words, for a power of a product, you can distribute the exponent.
Did you multiply those numbers together?
So, our last chunk here, we could, when we're simplifying these powers of products, if I give you two numbers here, I mean, you could multiply these things together. But 34 times 9 is a relatively large number. If I ask you to just leave this as in what's called exponent form, we could just use this property that was just above and make life at least relatively simpler, make a number that's manageable. Like 34 times 9 all to the 6th. Since this is only multiply inside here, we could just multiply each of the exponents by 6 on the inside. Well, what exponent do each of these numbers have?
1.
Okay, so then what's another way to write this? Could say what, 34 to the 6th power times 9 to the 6th power is one way to write this in exponent form. And then from there you could figure out what these huge numbers are and multiply them together to get an even bigger number. Or we can leave them in this nice notation. 4mn all to the 3rd. Is there any adding or subtracting in here? No. So that means we're good to go. We can actually use this. We could, if you want, you could put in what all the exponents are in here. 4 to the 1st, m to the 1st, n to the 1st. And distribute that 3. So our answer could be what? 4 to the 3rd, m to the 3rd, n to the 3rd. Note that each of these terms, the coefficient in each variable is raised to the 3rd power. Again, in exponent form, this is fine. Negative 2g to the 4th. What do I do for negative 2g to the 4th? Each of those have a first power, so I could just multiply 1 times 4 if each of those is 4. Our last one. I'll just do this one, I'll come back, and I think it'll answer your question. Okay, negative 5x squared. What's being squared in here? What's being multiplied by itself? The 5x. So then I have 5x squared should be the same as what? 5 squared times x squared. And this negative's hanging out on the outside. This would be the same as what? 5 times itself with the negatives hanging out on the outside. What's the difference? Notice that I have this negative inside of this set of parentheses, and I have this negative on the outside of the set of parentheses. Does anyone want to take a wild guess as to why I'm doing that? Lily? Where do the negatives start in this case? Inside. So where did the negative end in this case? Inside. Our negative is in the parentheses, it's going to stay on the inside. If the negative is on the outside, it's going to end up on the outside. Well, this looks a lot like that beginning of class today when we talked about what the calculator is thinking about. This is exactly why. So if you did say negative on this on the outside, you're going to square the 5, you're going to square the x, and then multiply it by this negative 1 that's floating around in front, or make it negative. Versus this guy is saying, take negative 2 and multiply by itself, take the negative 2 and multiply by itself 4 times. Which is what this is saying, keep the negative on the inside. Okay. I'm using order of magnitude. If I have 10 to the 4th boxes, 8 staples in each box, and I have 10 to the 2nd box of staples, how many staples do you have total? Well, this is just that first property, and it's exactly just Jack said. 10 to the 4 plus 2.
How much would that be?
10 to the 6 staples. This is a 10 to the 6. What's nice why we use powers of 10, because powers of 10 are basically a 1 with the exponent number of zeros. So this is a million staples. This is 1 with 6 zeros.
Is it kind of like scientific notation?
It's exactly what you're using for scientific notation. Yes. Orders of magnitude and scientific notation are very like hand in hand. So this is saying you have 10 to the 6th or a million staples.
So then if you have a negative exponent,